Hey guys, Ms. Peterson here, and welcome to AP Physics 2, Lecture 7-3, all about nuclear physics. So in this lecture, we're going to be discussing the famous equation E equals mc squared, a bunch of different nuclear reactions from fission and fusion and decay reactions, and talk about half-life. So let's go ahead and get into it. Okay, quick review. When we talk about nuclear stuff, we are going to be talking about things that go on in the nucleus, which is where the protons and neutrons are. Okay? The electrons are surrounded in a probability cloud of those quantized energy levels. Okay? And we will typically be working with isotopes. Okay? So atoms with the same number of protons but different numbers of neutrons. Okay? Now, this means that when we do the masses, we're not typically going to use the masses from the periodic table. The mass on the periodic table is the average atomic mass, okay? Because, for example, in a sample of carbon, you'll have some carbon with a mass of 12, some carbon with a mass of 13, some carbon with a mass of 14. It's all carbon because it all has 6 protons. And in a general sample of carbon, 98% of it is going to be C12, 1% of it's carbon-13, and we only use trace amounts of it for carbon-14. That's the one we use for carbon dating. So when we do these types of problems, we will need specific, very specific, very detailed masses, okay, with a lot of level of precisions. Okay. Now, what was happening was we were looking at nuclear processes, and we had our two laws, the conservation of mass and the conservation of energy. And once we were able to have technology that could measure our masses really precisely, we were seeing that the masses of our products in these nuclear reactions were slightly less than expected. Okay? We weren't getting a complete conservation of mass. And thus, the conservation of mass was replaced with the conservation of mass energy, where E equals mc squared. Okay, in a process, some mass might get converted to energy. There is energy contained in that mass. So if we lose that mass, we get the energy. So we have energy equals mass times c being the speed of light, which is 3.00 times 10 to the 8th meters per second squared. Okay. Now, also, typically when we do these units, we might be working in AMU, but on the equation sheet, it's actually just written as U. So 1 U is 1.66 times 10 to the negative 27 kilograms, which when we're working in electron volts, so with really, really small amounts of energies, we can actually just use a direct conversion of 931 mega electron volts per c squared. So note this 931 mega electron volts, that is energy. Okay, these are conversion factors. Okay, so yeah, we can convert it to kilograms, but now this is also giving us the conversion to convert it to energy. So if we're just looking for the energy in electron volts, we can just times it by 931 mega electron volts per c squared. The c squareds cancel out, and we just get that energy conversion. Okay. So the best example of this happening is in the sun. Okay. In the sun, there is a proton-proton chain reaction, and the general reaction is that we have 4 protons. A proton is typically written as just a hydrogen atom because it's just, if we have a hydrogen with a mass of 1, okay, that is just a proton. Okay, so label that, aka proton. Okay, and then it is going to turn into an alpha particle, which is a 4-2 helium. Okay. So here we can see that 4 times 1, that conservation of nucleon number, but we're not quite getting that conservation of of protons. Okay, we got 4 protons, and it only turned, by the end, there's only 2 protons. 2 of those protons turn into neutrons. Okay, and we can also see that in this reaction in these 2 E positives that are released. Those are the positrons. Okay, so plus those would be a 2, 1, 0. Sometimes you'll see it as a B positive. They did it as an E positive, so I will do it there. Okay, so that is a positron. Okay. And this one is that alpha particle. And so we're going to find the mass deficit in this reaction, okay? Knowing that the mass of the alpha particle, okay, the 4,2 is 4.0015 AMU, or U, and then the mass of the neutrino and the positron, we're going to ignore the mass of the positron for now, is negligible. Okay. So we're going to find the mass deficit, the mass lost in this fusion reaction. Okay, so for the mass deficit, I normally do it as change in mass. And in this case, it'll always be reactants minus products because you want to know the lost mass. If you do products minus reactants, you just get a negative number, which I guess makes sense because you do lost mass. So yeah, let's do it that way. Okay, so we have that mass will be the mass of the helium nucleus minus 4 times the mass of the proton, aka that 1,1 hydrogen. So the mass of the helium, they told us, is 4.0015 AMU. I'm going to convert that to kilograms because on our equation sheet, we only have the mass of a proton in kilograms. Okay, so let's go ahead and convert this number. I'm going to times it by 1.66 times 10 to the negative 27, and that gives us the mass of 4.0015 times 1.67, 67, not 66. Okay, 1.67 times 10 to the negative 27. So that tells us that the mass of that helium is 6. Okay, we had 5 sig figs there, so I'm going to keep that precision level. The precision level is going to be really important in these types of problems to keep it significant. You're going to need more decimals than you expect because the lost mass is so small compared to the actual masses. So 6.6825 times 10 to the negative 27 kilograms minus 4 times the mass of 1 proton, 1.67, times 10 to the negative 27. So with that, we get a mass deficit of minus 4 times 1.67 times 10 to the negative 27, a mass deficit of 2.505 times 10 to the negative 30th kilograms. Okay, that is the mass that turns into the binding energy of that alpha particle. Okay, so, and is the energy of the released photons and neutrinos in that reaction. Okay, so some of it goes into binding energy. We typically do that when we do have like protons coming together to form something, and that lost mass. So then E equals mc squared. This is the mass that turned into energy. Since we have it in kilograms, we'll keep it there with 2.505 times 10 to the negative 30th kilograms times the speed of light squared gives us 2.25 times 10 to the negative 13 joules. And there we'll have a lower precision because we only had our speed of light to 2 digits there, 3.00, as it is on our reference sheet. Yep. So That's how we use E equals mc squared. Let's do another example. We have a proton with its mass and a neutron with its mass combined to form a deuterium. Okay, the mass of the deuterium is that much. What is the mass deficit? Well, let's go ahead and find it. Okay, so this time we're going to go ahead and work in electron volts and U. Okay, this should just say U rather than AMU. It's stuck in AMU because that's what we used in AP chemistry. But our equation sheet uses U for unified atomic mass unit. So that mass deficit will be the mass of the deuterium, 2.01356, mass of the deuterium, minus the mass of the proton, plus the mass of the neutron, so minus the particles that combined to form it. Okay, and they're giving us the units to a high level of precision. So we got 2.01356 minus 1.00728 plus 1.00867. And we get negative 2.39 times 10 to the negative 3. So 0.00239 U. It's negative because it is the lost mass. Okay, the deuterium has a mass smaller than the mass of the proton and neutron. Why? Because some of the mass of the deuterium was used to bind the atom to create that binding energy. So if we have it just in the U, instead of, we're kind of using E equals mc squared, but we're really using that 1 U is 931 mega electron volts per C squared. So when we have that energy, okay, it's just forming energy, so I don't need to keep that negative sign. It's just showing that it lost mass. Okay, 239U. Then I can just multiply it by 931 mega electron volts per C squared. Okay, and you get .23 mega electron volts. So what is the maximum amount of wavelength that could be used to photodisintegrate a deuterium atom? Okay, so if we want to photodisintegrate it, we need to provide enough energy to break it apart. So 2.23 mega electron volts. Okay, and we want to know the maximum wavelength of light. So we know the energy of light is HF, which we typically rewrite as HC over lambda. Okay, and do I have it? Nope, I have it in electron volts, but not in mega electron volts. So I will have to convert there. But we can get our wavelength from HC, which is 1.24 times 10 to the third electron volts per nanometer, or electron volt nanometers, divided by 2.23. Mega is times 10 to the sixth, so times 10 to the sixth electron volts. So when we do that, we get, let me move that over real quick. Yep, and we get 5.56 times 10 to the negative fourth nanometers which would be, let's see, let's convert it from nano to milli. We know 10 to the negative 9 nanometers is 10 to the negative 3 millimeters. Okay, do we want to go milli or micro? It's negative 4. I think I'm going to go milli. Yeah, let's go milli. So that, and then, do I really need to do this in my calculator? Probably not. But sometimes I get a little mixed up, so I like to. Yep, we get 556 millimeters, which is what I expected. Okay, going up by an order of 6, so move that over there. Okay, cool. Okay, cool. Let's go ahead and look at some different nuclear reaction types. Okay, so there are a couple different types of decay reactions that you're gonna see. These are not the only nuclear decay reactions that exist. This is just some of the more common ones. Okay, alpha decay is when something emits an alpha particle. So that alpha particle is the 4,2 helium. Okay, that is the alpha particle. And then we go by conservation of nucleon number. So 86, and then I have 2 there. So that means I'll have 84 left. 222, 4 there. That means that there will be 118 left. 118 plus 4. 218 plus 4 is 222. And then 84 plus 2 is 86. And then number 84 on the periodic table. Got a periodic table here. Gonna look at who number 84 is. That is polonium. Okay. Now, for beta decay, it's when the nucleus emits either a positron or an electron. Basically, when a neutron changes to a proton or a proton changes to a neutron. And there's 2 different ways that you might see the positron and the electron represented. Okay, you might see it as a 0, 1, be positive. Okay, that's for the positron. Or the same thing, but with an E for an electron. Because the electron is typically drawn like that. Okay, but again, every now and then you'll see the beta instead of the E for electron. So carbon-14 is an example of this. So when carbon-14 decays, a neutron actually changes into a proton, causing the carbon atom to become a nitrogen atom. And it does this by releasing a electron. Okay. If a neutron that is neutral wants to become a proton, which is positive, it needs to lose its negative charge. And of course, I did it as a beta particle instead of as an electron. Okay. Now, fluorine actually does the opposite. Okay. Fluorine is one that where a neutron changes to a proton. So we'll have the 816, number 8 is oxygen, and the positron. Okay. So those are the 2 types of beta decay. Okay, we have a neutron changing to a proton by releasing an electron. And here we have a proton changing to a neutron by releasing a positron. Okay. Positrons have the same mass as an electron, but an opposite charge. They are the antiparticle of an electron. Okay. Now, often you'll see gamma decay with other decay types. This is where it releases an alpha ray when it decays. So, for example, carbon undergoes alpha decay. So it does produce the alpha particle and leave behind the 1838 argon. And then you'll just see it like this. It doesn't really have any mass, but that is just a gamma ray. And it doesn't even necessarily have to be a gamma ray. Really, it's just a photon. Okay. It is the energy that is released. Okay. One other type you might see is neutron decay. And every time you might also see neutron capture. Okay. This particle right here is the neutron. And so conservation of mass, we have 4 and 0. We need a 4 there. 13 and 1. We need a 12 there. And number 4 is still beryllium. Okay. So that beryllium just lost a neutron. Now, for the 3 main types of decay, alpha, beta, and gamma, sometimes you'll hear them talk about how penetrating they are. Okay? I know, fun. So alpha particles, because they're so big, they are slow, and they don't travel very far before they themselves tend to decay. And they can be stopped by things like a piece of paper or your skin, where beta particles tend to travel a little bit farther, but they are still stopped by things like a sheet of aluminum, where gamma rays can't be stopped except for by like a wall of lead. And that is why when you go to get an x-ray or something like that, the doctor who is exposed to those all day, every day, has to go behind that wall of lead or a metal wall in order to protect themselves from that radiation. Okay, cool. So some other nuclear reactions that we can do. This is fission, when a heavy nucleus splits into 2 smaller chunks. Okay, typically releasing energy. This is what we use in nuclear reactors. That should say reactors. Reactors. Okay, so let's see. We got 94, 40, and 54, so that's good. It's going to be a 0 there. 239 and 1, that's 240. 100 and 134, 137 is 237, so we need a 2 there, which must mean, 2, massive 2, but no positive charge. The way that probably is it is going to be 2 neutrons, 3 neutrons, 2 neutrons. 100 and 137, 143 neutrons, okay? There's a release of 3 neutrons. Okay. Oh, a neutron just has a 1, 0. There's also fission reactions. This is where 2 light nuclei combine to make a heavier one. This is what powers the sun, okay? Often produces lots of energy. They said 18.3 mega electron volts in that last step. We can also have just random reactions that they'll present you with, and we just need to use our conservation laws. So we got 8 and 1. Okay, 8 and 1 is 9, so that means we need a 2 there. 17 and 1 is 18, so we need a 4 there, so that must be an alpha particle. Slam it into a nitrogen to produce an oxygen atom and a proton, it looks like. Okay, cool? Okay, cool. Now, one of the other ones that you will see is annihilation reactions. In annihilation reactions, they're often between matter and antimatter, like a positron and electron, or they'll just tell you 2 particles combine and annihilate each other. In this sort of scenario, all of the mass is converted to energy. So positron, they each have a mass equal to that electron, so 2 times the mass of electron equals c squared, and it'll travel away as light, okay, or a photon. So we can calculate the frequency of that photon by the energy of that annihilation reaction. Okay, cool? Okay, cool. So let's go ahead and do a couple practice problems. Okay, here you're going to use conservation of nucleon number to fill it out. So we got 74 and 2. That's 2. And 72. And 180 and 4. So we have 180 there. Number 72 on the periodic table is hafnium. Okay. Go ahead and try the other 3. And then check your answers against mine. Did you get them right? Good. We have 2 examples of alpha decay and 2 examples of beta decay. And note, it's fine whether you used an E or a B in that notation. Okay. So in our nuclear reactions, again, that conservation of mass and conservation of energy is replaced with conservation of mass energy. The other true thing will be a conservation of momentum. Okay, momentum will be conserved in any nuclear reaction, and conservation of charge. Okay. Also, we typically consider these to be elastic collisions, unless it says otherwise. So often in those you will get conservation of kinetic energy. Okay. And not potential energy, because there's that nuclear strong force binding stuff and doing stuff and all sorts of things. And again, for solving them, we do them based on nucleon number. Okay. So let's talk a little bit about Compton scattering. Compton scattering is another nuclear process where we apply a lot of these conservation laws, and was another one of the big pieces of evidence for light as a photon and for this nuclear theory. So way back in 1923, what they basically saw was that if they shined X-rays on an incident beam, the X-rays that were scattered had longer wavelengths and less energy than before the collision, than before they collided with that material. And that change in the energy or the wavelength of that X-ray was determined or was affected by the angle at which it hit the surface that it hit. Okay, so let's go ahead and look at these equations a little bit more carefully. Okay, so here we have our equation for the momentum of our incident photon equal to h over that wavelength. Okay, and it collides with an electron at rest. That changes its angle, which sets the electron off. Okay, we can calculate the change in energy of the electron based on its change in speed, and its change in momentum based on that change in speed. Here they're showing it to you with the change in the energy of it, divided by c, the speed of light. So we can see that scattered photon now has a new wavelength. It has less energy. And the change in that wavelength is given by this equation right here. And that's the one that is also on your equation sheet right there. So it says that the change in wavelength of the photon that was scattered equals h over m naught c times 1 minus cosine of theta. Okay, where theta is that angle between where it was traveling and where it was scattered. H over, in our class, we'll only be doing this where it's colliding with an electron. So divided by that mass of the electron times c. So let's go ahead and look at an example here. A photon with a wavelength of 1.8 times 10 to the negative 11 meters strikes a free electron initially at rest in a head-on collision as shown. What is the energy of the incident photon? Well, we have the wavelength of the photon. So the easiest way to get its energy will be to do E equals HF, okay, where F is the frequency. And then we know we can also represent the frequency as C over lambda. So that gives us the equation that we use probably most often in these ones, HC over lambda. Yep. And HC, remember, is also on your equation sheet. You do not need to have all of these constants memorized. And for some reason, our equation sheet gives us both H and HC, which is really nice. We have our wavelength in meters, so we'll be using this HC, 1.99 times 10 to the negative 25th. 1.99 times 10 to the negative 25th joule meters divided by that wavelength 1.8 times 10 to the negative 11 meters gives us an energy of our photon of 1.11 times 10 to the negative 14 joules. Okay, so let's go ahead and determine its momentum. Okay, well, we have the equation right up here, so I'm just going to use that one, where the momentum of the photon equals h over wavelength. And again, on your equation sheet, we have h, 6.63 times 10 to the negative 34 joule seconds. And then this equation is coming from this one, okay? H over wavelengths give you P, the momentum of your photon. So again, we have H, that's 6.63 times 10 to the, can never remember those little exponents. Double check the equation sheet. 6.63 times 10 to the negative 34 to the negative 34 joules seconds divided by that wavelength, 1.8 times 10 to the negative 11 meters. And we get 3.68 times 10 to the negative 23, and we're talking about momentum. I could show you the units, but trust me that it is kilogram meters per second. Okay. Now, it has that momentum, okay? Again, we know that momentum. Hopefully you guys can kind of see where these equations are coming from in terms of this change in energy, okay? The change in that is due to the conservation of momentum, okay? H over C is, okay, due to the change in momentum. So will the photon's wavelength increase or decrease? Well, it's going to lose momentum and thus lose energy because, you know, it collided with something. It made the electron move, okay? So it must have lost energy, okay? So its wavelength will increase. Okay. Another way that you could look at this is through the equation. The change in the wavelength equals h over that mass of the electron times c times 1 minus cosine of theta. Now, if that photon's traveling back in that other direction, okay, from there, and then it's doing a zoop all the way to go back there, we call that a full 180. So we would have 180 degrees in for that cosine of theta, which would be 1 minus negative 1, which is 2. Okay, so in those head-on collisions is when you're going to get the maximum change in that wavelength. Okay, and it didn't ask us to calculate it, but we could calculate it if we wanted to. Let's go ahead and calculate the next one, though. If the photon instead struck the electron and scattered at an angle of 30 degrees, what will be the new wavelength of the photon? Okay, so this time we can actually change and find this out. Okay, so we have the change in the wavelength equals h over the mass of the electron times c times 1 minus cosine of that angle that it's scattered at, which is that 30 degrees. So we have h. Grab that from our equation sheet. Let's keep everything in joules. 6.63 times 10 to the negative 34. 6.63 times 10 to the negative 34 divided by the mass of an electron, which is 9.11 times 10 to the negative 31. Times c, the speed of light, 3 times 10 to the 8th. Or do they have it as 2.99? Why do I always forget that? Yep, 3 times 10 to the 8th. Okay. Times 1 minus the cosine of 30 degrees. Okay, and I'm going to go ahead and do this in chunks so you guys can kind of see a little bit of the scale of how this is going to happen. So we have 6.63 times 10 to the negative 34 divided by 9.11 times 10 to the negative 31 times 3 times 10 to the 8th. Okay, and that gives us a value of 2.42 times 10 to the negative 12. And that's a pretty small number, okay? This change in wavelength is never going to be that big. On times 10 to the negative 12th, that's not even a nanometer. That's like 100 nanometers? Picometers? It's on the range of picometers. But yeah, really, really small changes in wavelengths. They would probably not be visible to the naked eye. But we times that by 1 minus cosine of that 30 degrees, and we get 3.25 times 10 to the negative 13. And since it's our wavelength, we know that's going to be meters, because those were what our units in. But remember, that is the change in the wavelength. So if we want the wavelength final, okay, it will be the initial wavelength, which was 1.8 times 10 to the negative 11 meters minus this change, 3.25 times 10 to the negative 13, to give us 1.77 times 10 to the negative 11 meters. Okay, so a barely significant change in that wavelength. Okay, cool. Okay, cool. Okay, we have one more thing left to talk about with nuclear reactions, and that has to do with the rate at which they occur, which is given by something called the half-life. Now, the half-life is defined as the time that it takes for half of the radioactive actives to decay. So something that has a long half-life, it takes a long time to decay. Short half-life will release lots of radiation in the short term because it's decaying constantly. Now, this is a probability thing. So it's going to follow one of these like exponential graphs. And that rate is, like I said, it's exponential. So we're going to see that natural log in the equation. And we represent it with the decay constant. And isn't it fun that the decay constant has the same units as wavelength, and it's in a unit where we talk about wavelength a lot? Super fun. Love physics. Why is it like that? I do not know. I didn't make up the symbols. But we have the decay constant is the natural log of 2 divided by that half-life. Okay? And the decay constant is going to be specific to each individual atom itself, or actually each individual isotope of some of those atoms. Okay. Yeah. So one of the other ways that you'll see it represented is with this graph and with how much of it is there. So that's given by the equation N equals N naught times E to the negative decay constant times T. So when you multiply the decay constant by how many times you have, basically you're getting how many half-lives have passed, okay? Yeah. And both of these equations are also on your equation sheet. They're in that modern section, okay? Right down at the bottom, we have the decay constant, ln of 2, over the half-life, and then n, the number of particles, which could be in units of grams or number or amount or volume, okay, equals the initial amount times E to the negative decay constant times T, because, you know, it's decaying. So this is going to be a small number. So let's go ahead and look at some examples. Ooh, but before we do that, here's just some examples of the scale of half-lives. You guys have probably heard about carbon dating, okay? Carbon-14 has a half-life of about 5,700 years. So we can use that for things that are on the order of like tens of thousands of years old. where if we want something to track how medication is flowing through your body, we would want something that has like a really short half-life. Okay, like yttrium, 2.67 days. So that's going to emit radiation like at a lot quicker rate, and we can use it to see how things travel in the body. There's some with even half-lives of like seconds that we can use to track how an injection spreads in your bloodstream and things like that. Okay, so I'm going to show you guys two methods for solving half-life problems. For example, carbon-14 has a half-life of 5,700 years. Okay, that's not that precise. It's 5,730, but we'll go with it. What percentage of carbon-14 is left after 5 half-lives? So if you are a less mathy person, I love to solve half-life problems using a chart, where on that chart we have the number of half-lives, the time, and the amount. Okay, and these can be adapted to a lot of different half-life problems. But we always have time 0, where we have all of it. We're looking for percentage, so I'm going to do my amount in percentages. At time 0, I have 100%. After 1 half-life, which is 5,700 years long, I will be down to 50%. After 2 half-lives, now I have 2 half-lives, so 5,700 years times 2. Okay, it's been 11,400 years, and I'm now half again, so I'm down to 25%. Okay, and again, in this, you are adding a half-life each time. And in this one, you are dividing by 2 each time. Yep. So after 3 half-lives, that will be 1,700 years. Will be down to 12.5%. After 4 half-lives, that will be 22,800 years. It will be down to 6.25%. And after 5 half-lives, okay, which is times 5, 28,500 years, we will be down to 3.125%, okay, or half of 62.5%. Yep. Now, I could have also done this using this equation, okay? Let's go ahead and label this up here too, okay? N is going to be your amount, could be in any units, where N naught is your initial amount. Okay, T is your time, and this is your decay constant. And you just got to make sure that those have the right units, those same units. Okay, these units will always be like 1 time units, so inverse seconds, inverse minutes, inverse hours. Just depends on what type of scale, hours, days, years, your half-life is on. Okay, so using this one as an equation form, I would have N. I'm still working in percentage, so I'm going to go with my initial amount is 100. So 100% times E to the negative, I need the decay constant. The decay constant is the natural log of 2 divided by the half-life, which is 5,700 years. So that gives me a decay constant of, put that in scientific notation, 1.216, going to carry some extra digits there, times 10 to the negative 4 per year, so inverse years. Year to the minus 1 times the time, 5 half-lives. So we already calculated that over here. That is 28,500 years. Yep. So we plug that into your calculator, and don't forget the negative sign. Otherwise, you'll get a really funky answer, and you'll be like, that doesn't seem right. Okay, so we got 1.216 times 10 to the negative 4 times 28,500. Okay, we take E to the negative of that number and multiply it by 100. And we get an n of, what do you know, 3.125, which is the same answer we got using the other method. So both of them work. Again, the chart for some reason makes a lot of sense in my brain, and I can do that really, really quick on a little scratch paper where math requires slightly more thought, but it's pretty similar either way. Okay, cool. Okay, cool. Let's look at this one. A physicist has two samples of radioactive material with these properties. We have a sample of mass 1 with 52 grams and a sample of mass 2 which has a starting mass of 200 grams. After 12 days, both samples have approximately the same mass of radioactive material remaining. The half-life of sample 2 is approximately what? Okay, so we're trying to solve for the half-life here, okay? And we know that they have the same mass remaining. Now, again, we could use this with the table or with an equation. I'm going to go ahead and show you guys how I would do it with a table first, because I think that makes a little more sense conceptually. And then it's with an equation and doing a derivation. So if I have sample A, okay, and sample B, and then we're going to have the thing that's going to be the same for them both is the time, because, you know, time is time. You can't change time. But we have the number of half-lives, the time, and the amount. And then for part B, again, we got the number of half-lives, time, and amount. And let's go ahead and put in everything we know. We know sample A started at 52 grams and has a half-life of 3 days. So after 3 days, it would be down to 26. After 6 days, it would be down to 13, okay, etc. And then we have part B, which we know started at 200 grams, okay? We don't know its half-life, okay? But we do know after a time of 12 days, okay, the amount remaining will be the same. So, well, let's see for sample 1. I'll change color so you can see the difference here. Where is it at after 12 days? Well, 3 half-lives would be 9 days. It would be down to 13 divided by 2, which is 6.5. Okay. After 4 half-lives, it would be down, that would be 9, 11, 12 days. Oh, 12 days. We'd be at 3.25 grams. So that tells us that after 12 days, this one is also at 3.25 grams. So how many half-lives is that? Well, we know it's going to be more than 4 because we started with 200, okay? So I'm going to go ahead and move this on down and then just fill it in until I get there, until I get to 200. Or backwards, we would have 100 grams and then 50 grams and then 25 grams and then 12.5 grams and then 6.25 grams and then about 3.25 grams. Okay, so that's 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives, 5 half-lives, 6 half-lives is 12 days. Okay, so that tells us each half-life on its own must have been 2 days, because then it'd be 2 days, 4 days, 6 days, 8 days, 10 days, and after 12 days, these would have the same. Okay, so that half-life is 2 days. Now, again, very conceptual way of solving it. This is how we did half-life problems before these equations were added to the AP Physics 2 equation sheet. But let's go ahead and solve this using the equation, because that's probably going to be a little easier. Because, hey, it says their amount is the same. So, really, we're just solving for If their amount's the same, we can set these equations equal to each other. The time is the same, they just have different decay constants. And we know one of them, so we can solve for the other. Okay, so first, let's go ahead and find the decay constant for sample A, which will be the natural log of 2 divided by 3, which gives us a 0.231, and that'll be days to the minus 1. So in that equation, we have that n equals n naught e to the negative decay constant times time, almost called a wavelength. And it says that the amount is the same after 12 days, okay? So we can set NA equal to NB. So for for sample 1, we have its initial amount, which is 52 grams, times E to the negative 0.231 times 12 equals our other initial amount, 200 grams, times E to the negative decay constant, which we're trying to find, times 12. And now we algebra, and hopefully we get 2 days. Let's find out. So first we have 0.23, I do it 0.231 times 12, negative E to the negative of that number, times 52. So then I got 3.252, which is the amount remaining. We had already gotten that right over here, equals 200 times E to the negative decay constant times 12. So I'm going to divide that by 200. And we get 0.01625 equals E to the negative decay constant times 12. To undo the E, we take the natural log of both sides, which cancels that out. When we take the natural log of that number, we get negative 4.119 equals negative decay constant times 12. And the negatives cancel. We have 4.119 divided by 12, and we get a decay constant of 0.343. Okay, now we know the decay constant equals natural log of 2 divided by the half-time. So the half-time will be the natural log of 2 divided by 0.343. And what do you know? We get 2.02 days. So just slightly off from what we got using that chart method. And that's nuclear physics. Okay, cool? Okay, cool.